We are going to talk about CubeRover. What is CubeRover? So it's a semi-autonomous moon rover which has size, weight, power and cost constraint. Size is like, it fits in a 30 centimeter cube, and it weighs 10 kilos, and it's not self-charging, so there's a huge power constraint on the CubeRover. And there is a Tegra K1 mounted on it, and we are using OpenCV's C++ RGBD odometry implementation as our baseline check for performance and correctness. We are using Kinect's RGB and depth images for our input. Camera tracking. So what is camera tracking? It's finding the position and orientation of a robot using the images it captures. And in this problem, we take two consecutive RGB and dense frames as our input, and our output is our estimated camera motion, which is a rotation and a translation matrix between two consecutive frames, pair of images. The camera tracking can be done in two ways. One is sparse and one is dense. Sparse, we take a couple of hundred or so features, like the green dots you see here, and we measure the difference and calculate the rotation and translation of the camera. But in dense, we use all the pixels and find the correspondence between the two pixels, and this proved to be giving better accuracy, but it is computationally more expensive. So the challenges that we have faced here is we have to make this real time, and the algorithm that we used is estimating the camera motion iteratively, and there's a large chunk of code, like quite a few chunks of code that is serial. Most CV algorithms have filters and masks which don't go too well with the SIMD on the Tegra. It has a lot of divergence, and also we wanted to plug our implementation back in OpenCV and use its implementation, so that was another challenge we faced.
So to give a high-level overview of the algorithm, so we have a color and a depth image. We can use the depth image to find the 3D points of the pixels in the image. Then we have an estimate of the rotation and translation. We use that estimate to rotate and translate the 3D points. We transform the 3D points, project it back onto the second image, and now we have two second images, something we think is a second image and something which is actually a second image. And now we iteratively minimize the error between the two images. Yeah, sorry.
So we process depth images and the RGB images. We use Gaussian, we convolve every pixel with the Gaussian kernel, and we downsample the images. And at the same time, we also process depth images. We are only considering those depth values that lie in a certain threshold. And then we calculate image gradients using Sobel filters, which was just explained in the previous presentation. And so this is our performance. We launched two kernels for processing the depth images and the gradients and pyramids. It had quite a bit of divergence involved in both the kernels, but we could club both gradients and pyramids because launching, we wanted to avoid kernel launch overhead. And this had some serial code, but it still proved faster than launching two separate kernels.
So now we come to the chunk of the algorithm. We've just finished pre-processing the images, and now we have to run a loop in which first we compute correspondences between two images, then we compute the square difference between the correspondences, and then we compute the motion. So take link for example here. So you can see that the camera has moved toward link from the first to the second view. And I've drawn a few correspondences which are actually good, but initially our correspondences will not be that good. So how we find correspondences is, suppose you take link psi and you project it to 3D, transform it, and project it back and say it lands here. And that's the correspondence of this image to this. So that's how we calculate correspondences. And there are two ways to encode correspondences. Now, we could have taken a huge mask the size of the image, and for each pixel, we could have stored what pixel there it corresponded, what coordinate there it corresponded to. But we found that there were about 20,000 correspondences out of 300,000 pixels. So it would have caused a lot of divergence in the computation. So the correspondences are scattered all over the image. So instead, we sacrifice a little bit of the parallelism here to put in an atomic construct and make the correspondences into a dense, stuff the correspondences into a dense array. And that really helped in the next couple of steps. So computing square difference and computing motion they work only on the pixels which have valid correspondences. So we needed, so the sacrifice in the previous step really helped here. And we saw a lot of, even though this wasn't unbelievably parallel, those two were pretty good. So we were quite happy. And if we used the mask, the huge image mask, those two performed pretty badly, though this was better. So overall, we were quite happy with that decision. And the overall performance of the algorithm, this is the entire algorithm for a pair of frames. So the overall performance, so OpenSeries, as we mentioned, took about 750 milliseconds to run, process 2 frames. Ours took about 250 milliseconds. So we were 3 times faster than OpenCV, but more importantly, from the CubeRover's point of view, we were almost real time because the CubeRover moves at 15 centimeters per second. Though of course, we wanted like 20 hertz speed, but we're getting about 4 hertz, which is okay for the CubeRover. We're still not totally happy, but this is all right. Yeah.
So the rotation and translation that we found with our algorithm, we applied on frame 1, and we tried to get frame 2, and warp frame T is what is our result. Where can we do better? So we could have used unified memory that's there on the Tegra, but the OpenCV's data structures used MAT, which we could not have used for kernel launching. So we had to do a CUDA memcopy to get the correct right format, which was GPU MAT. And since there was a lot of serial operations and it was an iterative estimation, I don't think we could have done better there. We could have used CUDA streams, but since the images were not that huge, the data transfer could not have been that efficient when we are trying to do a computation at kernel simultaneously. So this would be useful in huge images, but we didn't use it here because our images were really small.
Yeah.